a lot of AI talks in the conference, isn't it? This may be totally different. I'm talking about the real world problem solving, some of the most critical or most business impacting scenarios that we encountered in the field. Thought it would be great to share with this audience. A couple of messages I want to pass through this slide deck is one is many a times the business impact of the problem could be orthogonal to the real complexity of the issue that we are solving. So don't be biased or don't be pressurized by the impact that the client is seeing or the executives are putting on you. Stay focused, look at the problem, apply logical reasoning, apply the necessary thinking, critical thinking, and other ingredients that is required for the problem solving. That's number one. Number two, we hear a lot of questions around AI, non-AI kind of things. So one of the main thing I want to state is whether AI or non-AI, the creativity, the problem solving, the logical reasoning kind of aspects will stay. That has to stay because that requires extreme cognitive activity, including the comprehension, the interpretation, the analysis, the synthesis, and the creation. So all these things coming in sequence is absolutely necessary, required for problem solving, and that will stay with humans for a long period of time. So if I may quote Einstein's famous quote, which is in this context, is engineering is 1% development and 99% problem solving. So problem solving is absolutely critical. And let's look at some of the problems that we solved. It's not just I solved all the while. I have my ex-colleagues from IBM, Pushkar and Jayashree. We solved it as a team through various problem-solving activities. I organized these problems in the increasing order of complexity. Start with a very trivial one, and we look at some of the more complex ones. Some of the problems are a repeat from the last year. I got great feedback, so I thought I will include that this year as well to reinforce the learning. So the first one, pretty trivial. It's a client that reported severe performance degradation when they developed a new web application, which had highly concurrent workloads. We used IBM Samaru JVM, which is IBM's JDK, and the JVM has a default GC policy, which is GenCon, generational concurrent. So we looked at the problem, we analyzed the verbose GC logs, and we found that there are very, very frequent minor GC that's happening, followed by frequent major GCs. So what would be the first problem analysis step that you would perform? Definitely look at the rate at which the new objects are getting created. Generational concurrent is based on the principle that objects die young, especially that is true for the web workload. The transactions keep coming from the user, and once the transaction is over, all the objects that are created as part of the transaction should be eligible for collection. So that's where the minor GC, the major GC comes into the play. Once all the elements of the transaction is over, could actually wipe the minor heap, the nursery or the Eden, whatever we call it. So the obvious solution for this is look at the transactions volume, look at the number of objects that are created, part of one transaction, estimate the size that is required for each of these objects, and then multiply it with the number of concurrent transactions that is allotted for that particular node, and add a little bit buffer and assign that as the minor heap size. So it's pretty straightforward. Any questions or comments on this? The actual flag might change based on the JVM, but fundamentally you adjust the heap size according to what the transaction that are coming. So everything is contained within the minor GC. When the major GC kicks in, it takes a lot of time and space to clean up the garbage. Second one, this is Apache Spark on PPC port. So here what happens is the client, an enterprise mobile client, uh, developed a new mobile application and purchased a number of hundreds of IBM PPC servers. PPC high-end servers are known for the performance by virtue of the RISC architecture and high-end performance for server-grade systems. Uh, they ran their application, they reported problem, and then they went back to the basic sanity test, which is called uh, word count problem. That's like the hello world problem in Apache Spark. Just feed in a large sentence and then break it into sentences, break it into words, assign each word or each cluster of words to individual worker nodes. Worker nodes will compute the number of words and bring back to the main engine and reduce it. Typical map reduce algorithm. Very simple test was failing. So when we looked at the stack trace, it was very consistent. When we ran the the MapReduce problem into PPC, we got the same exception. What was happening is the serializer, when individual worker threads were assigned with the task, they receive the class and the object. Before applying anything on the object, they need to pass the class, and the class itself was not coming properly. The 4 bytes were coming in the reverse order. So obviously the inference is that the moment you see that bytes are coming in reverse order, the first suspect is the byte ordering. There are concept called little endian and big endian, by which you specify the order in which the bytes should be deciphered or bytes should be processed to make the number. So that itself is different between PPC and Intel. So what is the fundamental problem? Fundamental problem is most of the open source projects were developed in Linux on x64 and they were never tested on other platforms. The moment the client tested that, they got the very basic failure and they threatened IBM to take back all the servers. If you don't solve the problem, take back all the servers. It's 70 million was the deal at stake. So the entire department, not only Java team, but all the system programmers, the Spark people, the whole of the software component team were called out, and we had critical situations, day in and day out solving, figuring out what's going on. But what it takes is just one line change. The specific serializer that is getting the class data or the object data should consider the platform, underlying platform where it is being run, and sequence the bytes in specific order which the platform expects. So number of leading zeros should be changed to number of trailing zeros for PPC. For Intel, it should be the same. So one line change, $70 million. Just reiterating the original message I said, business problems are not necessarily aligned completely with the complexity of the problem. So keep that in mind, stay focused. Any comments or observations? I'm sure you would have seen similar situations, not necessarily the exact stack, but problems, patterns could be pretty similar. The third one, little more complex, JUC hang. JUC stands for Java Util Concurrent. It's an attempt to implement the concurrency at the Java level rather than calling the OS. OS is heavyweight. You need to have the context switching. You need to call the conditional wait and so on and so forth. So JUC, completely Java based. It has a simple atomic variable, and anybody who wants to synchronize on a shared data first acquires the atomic object and then go ahead and do the operation. The other threads who want to operate on the same data come and check the value. If it is 1, meaning it's engaged. If it is 0, meaning it's free. So based on that, they wait on a cooperative way. So that's how the JUC works. So It was from a famous e-commerce customer. Now, e-commerce, as we know, it's worldwide. So one of the user pattern that we observed is if you go to the e-commerce to purchase something, you don't see the site. Maybe if you're buying $1,000 product, you will wait for a day or so because it's your favorite. But if you're buying a $10 thing, you don't see the site. If it is a cheap one, you just go to the next one and buy that. So $40,000 per second was the impact that was reported by the customer because of the hang. So the more the server is hung, the number of users dropping out is huge, and that business is never returned. It's gone. It's purchased from some other vendor. So here is the stack and the failing context. The first is the typical stack of the parking thread. You see if any threads are engaged in the JUC synchronization, you will see them as parked in this particular state. So we see 1,000 threads in the 1,000 plus threads in the parking state, and definitely when they are parked, they should be waiting on some object. And we looked at which object they are waiting for, and we saw that that object is owned by another thread, and the natural expectation is that that thread would be doing something with the object or entered some critical section with that lock on. But surprisingly, it's doing something else. It doesn't have that particular lock. So basically what it means is you have a number of threads waiting for a lock to be released, but the lock has no owner. And this line number 597 is the atomic variable which I was talking about. That's the focus in this problem context. If the threads are waiting on that particular object, then this state should be on. It should be 1. And some owner should be there. But we don't see the owner, and we see the value of the state variable to be 0. So that was the tricky scenario. If it is 0, the question is, why did 1,000 threads got into an impression that the lock is held by somebody? Any thoughts? Yeah. So the e-commerce site, the applications, web applications don't directly access this state variable and put anything. They will have higher levels of abstractions, APIs, Spring Boots, WebLogic, WebSphere, Open Liberty sort of framework will be there. On top of that, other application layers, and finally the e-commerce app, right? So they don't directly deal with that, but eventually some code should be accessing this to get access to the JUC. So we did a lot of analysis around that, and we saw that threads are parked, and we actually also worked with the JUC author. His name is Doug Lee, who actually is the creator of this particular module. He said this state is impossible. If threads are parked, then the state variable should be on, and that should be handled by some thread. If that thread is releasing, the bottom thread is releasing the lock, then it should be back to 0. And then the two are consistent, but the first one is not consistent. First one should be able to get on and access the lock and do away with their work. That doesn't seem to be consistent. So the key, the inference is, look at the access specifier of the state variable. It's volatile. So what does volatile mean? Anybody? Any thought?
But the simple caption, when we write goes directly to the real setup.
Yeah.
Caches.
Exactly. Yeah. So if variables are non-volatile, that means this is not used by multiple threads. If you see a necessity for the variable to be accessed by multiple threads, which is exactly the case for JUC, the field should be declared volatile, and the compiler or whoever is converting the code into bytecode or native code should implement that particular specification. So in this particular case, answering your question as well, after the fact, we understood that in this e-commerce site, there were several calls by single thread to perform some batch operations, not in a concurrent way. And under the cover, Java has something called just-in-time compiler, which profiles the application and makes certain assumptions. And it made assumption that this part of the code is accessed only by one thread. So though the variable is declared as volatile, the volatility is not actually required, because when multiple threads are not present, volatility is a burden. It flushes from the cache, and caching is an optimizer. If you don't keep it in the cache, you pay a penalty, performance penalty. You put it in the main memory. So JIT is supposed to be accelerating the performance. So in an attempt to accelerate the performance, it actually removed the volatile keyword. Sorry, the volatile nature of the variable, because it understood that there is only one thread that is accessing. But suddenly, there is a spurt of multi-thread activities, and before the JIT compiler could actually understand that there is a multi-thread access, and now I need to revalidate the original assumptions and recompile the code, the damage has been already taken.
It is that great.
Multiple ways. Ideally, the thread dump shows which thread is holding the lock. In some, at least IBM Java dump shows that. But if that thread dump is not showing who is owning this, you may need to resort to something called system dump. That is a low level dump, in which if you analyze the call stack, you will see which thread is holding this lock at what frame, etc. If that is also not available, every Java object internally maintains a field called lock. So by looking introspecting into the object, you can figure out whether this object has the lock in or not. So in this case, access the JUC object, the abstract synchronizer object, and see what is the state of the object. Yeah.
It's that shift that
Right. Yeah. So there was a glitch in the JIT compiler, the way it understood the multi-thread reentrance and the definition of volatile, when it should be switched back, things like that, and that is how it fixed. So the normal 1 to 0, 0 to 1 is an atomic operation. Just need to assign one value from 0 to 1 or 1 to 0. You need to prefix it with a native primitive called lock exchange in Intel, so that that change or the movement really get flushed into the memory rather than in the cache. All right. Any other questions on that? Yeah. Basically workaround. Yeah. I mean, the moment we saw that this state is inconsistent, I mean, through normal Java semantics, this is impossible to reach. We got the conviction from the author itself. Obviously, the first suspect is the JIT compiler. So the first workaround is to skip JIT, though with a penalty of reduced performance, and that worked fine. Yeah.
Then the Pfizer that there was multiple.
Yeah.
Wouldn't the JIT compile both we go then we compile?
Yes.
And during this period.
Yes. So there was a concurrency issue, that the timing issue. It definitely noticed, but it didn't get the leeway for doing that and bring in the new compiled code.
Did you were you able to reproduce it?
No. I mean, we had several types of tests. None of those were able to reproduce it, because this happened in the peculiarity of the e-commerce site, the way the workload is coming, like single thread access to a variable for a long period of time until the application saturates and gives sufficient profile information to the JIT compiler, and it compiled to the maximum optimization level, and then comes the real workload. So that scenario, obviously now looking back, we know that we need to add such test cases in the product. Initially, we never had such insights.
But maybe can be
Oh, I don't know.
when it would take a while
Yeah,
for the certificate
right,
was the figure then I would go
right.
keep performance
Performance system test, so many different variations of test exist, but we continue to get problems.
exactly.
Yeah, so once we understood that this is what is causing the problem, then it is easy to recreate in a small test case, right? We could bring in the same simulation by doing one thread activity at a time and allow the JIT compiler to saturate profile driven. We have various flags for the JIT verbose options and understand that, okay, at this point, it's an highly optimized, and we can check the compile code to see the volatility is not inserted. So all those things are possible. Yes. So anybody knows about RSS, resident set size? This was produced in Node.js, but it's equally applicable for any platform, any runtime. So the clients reported that they had a, again, highly concurrent workload, which one batch takes a lot of memory, maybe a lot of computations, a lot of memory churning operations and things like that. And they were expecting all the memory to come down once the transaction is over. So it was in GBs. They know that all the transactions are over, but the memory was staying at high where it was. They have no problem with the memory staying high, I mean going up, because they precisely know this much memory it takes. But the problem is once the transaction is over, even after seconds, minutes and hours, the memory is still staying there. And they check their application code base to see if there is any caching that is happening, any large chunk of object is being pushed into some arrays or list or some collections. That's not there. They absolutely check their heap dump and they realize that there is nothing. Application wise, everything is clean, but still the RSS is staying at top. RSS is a specialization of the virtual memory. Virtual memory is the amount of memory allocated into the program. RSS is the active memory used by the program. Now, why we care about RSS? If you are running in the cloud, they bill based on the RSS. They bill based on the resource usage, and memory is one of the resource, and they look at the RSS, right? So that, according to cloud vendors, that truly represent the activity of your process or the memory utilization by the process. So that is why they were concerned. They had 200 plus installations in AWS. So it means a lot of money. GBs of memory kept on hold. No transaction is running, especially banks, right? They don't run in the night, certain geography. So it was kept at high. That was a problem. For this, we spent a lot of time. We couldn't reproduce the problem at hand. We tried various simulation testing. Every time we tested, the memory was coming down once the transaction was getting over. We tried different languages, including Java, C, C++. Nothing helped us. Then we started working very closely with the clients. We started simulating one by one the configuration, the application's nature, the boxes, like the hardware configuration, different architectures, so on and so forth. And finally, when the memory configuration of the client was matching with our system, like 120 CPUs and I think 30 TB of real memory. That's the configuration we got, and we ran a simple C program. We got the same behavior. So we had to allocate in chunks, we had to allocate in different numbers. Every time we allocate memory, it was just pinned towards the process. Once we deallocate, it doesn't come down. Your inference is right, written over there. The point is, there is a misconception about RSS. We believe once the program deallocates it, frees it, the memory should come down. That's not happening. The RSS comes down only in response to the demand in the system. If the machine is very lightly loaded, the RSS stays on top. That is very tricky, but that is the fact. Why we were never able to recreate? Because our systems were having light virtual memory and we had so many other processes running in the client server. This was the only process running. They had ample amount of virtual memory. So whatever the RSS went up, it stayed there. There was nobody else demanding the memory. So it stayed with the process. What does this mean? This means huge. This means huge to any deployment that is on the cloud, and for those deployments which is charged by the RSS. We talk to the Linux kernel folks, we talk to various other folks, and they say this is the remedy.
Very good poets.
This is OS, yeah. So we trust the OS to say this is the memory allotted to me, but that's not trustworthy, is what the inference is. I talked about this last year, thought this should be informative because it's not just for Java or Node.js, for anybody.
That's maybe talking about it.
Yeah,
It's for listen this week
yeah.
or go to
RSS is retained. Yeah, sure, yes. Yeah, it also depends on the cloud configuration. So for example, if the cloud is so smart that if your process is not really needing that much of memory, they may cut short the container allocated memory to only that much, or maybe there is some optimization in which you will be lucky because you don't really use it, so the container is shrink to that size. But some VMs, we don't know the VM policies. They you wanted this much, you allocate for this much, and then just stay there. It's dedicated for your application. Just looking at the time. Oops, we are already 4 minutes. Okay. The last one, which is very complex, we call it famously R11 corruption. So 15 or 16 customers, I think 17 customers reported this problem once in their lifetime. What is happening is they get crash. They get invalid method exception or incorrect method exception, whatever. At the onset, what's happening is Java method is calling a wrong method. And when the wrong method is being called, it will access this pointer, the receiver object, and that object doesn't have the desired fields or methods, so it crashes big time. That's the manifestation. So very, very tricky. And the to make it more complex, it happens only once in a lifetime. So we analyzed the dump multiple times. Multiple folks looked at it and they said this is absolutely not possible. And there was suggestions to replace the hardware because every time the problem happens, the problem is manifested in a bad value in the R11 register. So the recommendation was to change the hardware, thinking that the hardware is at fault. Some flip-flops or some low-level transistor may be having some sort of hardware issues by which the value is getting eroded, was the assumption. And clients, though unwillingly, they replaced and they never found the problem. But we started getting the same problem from different clients, and we applied. I mean, some clients would definitely refuse to replace the hardware. It's not cheap, right? the high-end servers. So we were forced to look at it again and again, and we started applying some logical thinking. If R11 is at fault, Java is not the only process that is running in the system. Java comes much later. The OS gets booted up, and so many other batch jobs, shell scripts, and other daemon pro. You just do ps minus ef, you get hundreds of processes. Everybody make use of R11 register in one way or the other. So if R11 is at fault, it would have crashed a million times in a second. Yes. Why it is crashing only for Java, and why it is crashing only in a specific way when there is a method calling another method and the call is bad. So that was the first logical thinking that we applied, and we were convinced that no, hardware is not at fault, it's the software, right? Then we looked at JIT. Obviously JIT is the primary suspect here, because usual Java semantics, this bad call is not possible. It will be caught by the compiler. A calling B is not in the semantic context. It's not possible. So we looked at other platforms, no issue. We looked at JIT skip, no issue, and simple applications, no problem. Finally, we got the first hint. This application, which every 17 customers who had failure had made use of a specific package, and that package had a lot of interfaces. So when there is an interface method invocation, that's where the problem is happening. Here is the actual context. I don't know how many of you are well versed with assembly, but this is very interesting. Let me quickly go through that. We have a cache, we have a cache reader, cache writer, and a cache. So when you invoke an interface method, what you do is you look at the receiver object and see if it matches with the previous context. If it matches, then just get the method that is associated with the class and invoke it. Otherwise, you need to go through the whole of the class hierarchy and figure out whose class is matching with the current receiver object, and then iterate through the class and figure out the method and invoke it. It's a time-consuming activity. To optimize that, we put in a cache. So every time we hit a method, we put the method and the class as a pair and store it in the cache. The reader, instead of going to the devirtualization, just look at the cache. If you find a matching class, just pick up the next field, which is a method, and invoke it. And the BL, the branch and link R11, this is the faulty method. That's where we got a bad method every time. So, anybody can suggest what is wrong with this code. I'm sorry, we don't have much time, but... Huh? Yeah. One could argue that the store is not atomic. You are storing the class first, the method first, and the class second. If you store the class first, what happens? Another thread comes and stores the class first, and another second thread comes and read it. They will match the class, but pick up a wrong method, because the method is a previous method. So for that, we store the method first, then the class. So if you match the class, you will not find the match, right? So that way there is no problem with that. But there is a problem lying in the way we are storing in the cache. That's not sufficient. It should happen together. If it doesn't happen together, what happens is, if you store the class first, if you store the method first, if you store the class second, this is our request to the processor. But the processor has something called instruction scheduling and instruction pipeline. What it means is looking at the store operations, if they are completely disjoint, so storing at two different locations, they are not dependent in any way from the processor point of view. From Java point of view, yes, but CPU doesn't care. Two different operations, two different memory locations. Which memory address is already with me? Which memory bus is free at that point? Based on that, it can tilt the order. So that is called instruction pipelining and scheduling. So in that process, the class got stored first, then the method, and at that moment, another thread came and read the class. The class is matching. It picked up the method, which is wrong, which is a previous method, executed it. We got the invalid method exception. Very, very complex and tricky. we took years to solve this problem, and there was no fault at R11. R11 was good. Problem was with our code. So the solution was to insert a sync operation after the first store, by which we are telling go hand in hand, go in this order. So that's pretty much it is. I want to reiterate the fact that business problems are not necessarily in line with the technical complexity of the problem. Don't get confused or don't lose the focus. Stay focused on the problem. Look at the logical reasoning and other problem solving skills. Number one. Number two is AI or non-AI. Problem solving happens to be the most critical aspect of software engineering, and um, continue to migrate, continue to embrace problem solving skills that will make us super critical. Thank you so much.